Greetings. This is going to be a presentation on logic, and in this presentation I will be looking at both formal logic and informal logic. It's kind of a gloss over this. I mean, we'll cover a lot of topics, but we won't get into too much details in any of them. But I just want to go over certain terms and compare and contrast the different kinds of logical reasoning that we'll be looking at. So let me begin by sharing my screen. Share screen. And where's the screen I want to share? I think this is the one I want to share, except, wait a second. So I didn't, there. Okay, so this is logic and critical thinking, analysis and evaluation of arguments. So one reason to study philosophy is because it does help to train one to think critically and evaluate arguments well. It makes an excellent pre-law major for that reason. For those of you who are maybe interested in going on to law school, you probably already know you can major in anything and go to law school, so you don't have to major in philosophy or whatnot. But this is a good major of philosophy because there's so much emphasis on clear thinking, on argument analysis, on defining one's terms and this sort of thing. And these are good skills to have. Since doing philosophy rests largely upon arguing, it's not surprising that philosophy has a branch devoted to nothing other than the study of arguments, and that branch is logic. So logic is the branch of philosophy which analyzes and evaluates arguments. And by arguments, I have in mind verbal attempts to persuade. So, you know, we use the word argument for any number of things. If I'm saying, shut up, and you, no, you shut up, go, no, you shut up. Well, there's a sense in which we're arguing, but that's not really what we're interested in when we're doing logic. So the anatomy of an argument, arguments consist of premises and conclusions. And this might be fairly obvious already, but it's sometimes good to even state the obvious when you want to make sure you've covered your bases. So premises are those reasons offered in support of the conclusion. And the conclusion is what it is you're trying to persuade your hearer to believe, or what the arguer is trying to get the audience to accept as true. Now, many philosophical arguments will start off with the premises, they'll come first, and then the conclusion is drawn at the end. But this isn't always the case. Both inside and outside of philosophy, sometimes you will find that the individual might start with the conclusion. We should have a universal healthcare system, and here's why. So notice I started with my thesis, my conclusion, and then I proceed to give reasons. Or sometimes I might start by building my case and giving premises, draw my conclusion, and then supplement that with some additional conclusions. My point is just this: don't assume that simply because the sentence comes at the end of the paragraph that it's the conclusion, right? Well, how do you determine what the conclusion is? You want to ask yourself, what is this person trying to prove, right? Of what point is this person trying to convince me, right? Whatever your answer to these questions, that's the conclusion. Then ask, what reasons, if any, have I been given to believe this conclusion? Whatever your answer to that, those are the premises that are being offered. Note now that sometimes the conclusion or even some of the premises can be implied but not explicitly stated. So there's the text of the argument, either the spoken or written text of the argument, but then there might also be unstated, unwritten, verbalized, implied premises or even conclusions. Now, philosophers, like lawyers, usually consider this a weakness in an argument because it creates a certain vagueness and ambiguity. It's not explicitly stated. And so if you think about a lawyer drawing up a contract, they don't go, oh, you know what I mean. No, they don't go, you know what I mean. They go, no, put it in the contract. Everything's explicitly stated. So consider the following argument. All US states have 2 US senators. Therefore, Florida must have 2 US senators. What's the conclusion of that argument? Florida has 2 US senators. What's the stated premise in that argument? All US states have 2 US senators. But notice there's an unstated premise there, one that you need in order to draw the conclusion from the premise set. And the unstated premise is Florida is a US state. So again, the conclusion is Florida must have 2 US senators. The tip-off word, of course, was therefore. The stated premise was all US states have 2 US senators. Again, but there's more going on. The implied but not overtly stated premise is that Florida is a US state. And it's only, that's the only way one could get to the conclusion from the stated premise. You'd have to supplement the stated premise with the unstated one in order to arrive at that conclusion. So the full argument is actually this: all US states have 2 US senators. Florida is a US state, therefore Florida must have 2 US senators. That's a perfectly fine argument. Consider by contrast this argument: all US states have 2 US senators, therefore the District of Columbia must have 2 US senators. Well, that argument does not work because it assumes falsely that the District of Columbia is a US state, but it's not. Although DC has a larger population than some states, the district is not one of the 50 states, and it has no senators at all. Sometimes the conclusion can be implied, but not directly stated. So just as a premise might be implied, you might have an implied conclusion. Consider this argument. I'd say, Mary would never miss her best friend's wedding unless something terrible had happened to her, and she's not here at her best friend's wedding. Well, you wouldn't ask the speaker to say, what's your point? Well, it's pretty clear what her point is, right? Her point is that something terrible must have happened to Mary. Why? Well, because she'd be here if something terrible didn't happen. She's not here, therefore, right? But she didn't explicitly state it. So there's an instance where the conclusion is implied, but not explicitly stated. Often implied premises or implied conclusions are so obvious that they hardly seem worth mentioning, maybe even in the preceding example. Consider this: of course some cats are affectionate. Why, my calico is extremely affectionate. The conclusion: some cats are affectionate, follows from the stated premise, my calico is extremely affectionate, only assuming an unstated but necessary premise, my calico is a cat. But in this case, it's obvious that my calico is a cat, if you know what a calico is, I guess. So it would be silly to actually state that in normal conversation. Now, while sometimes an unstated premise is a no-brainer, as in the preceding example, and it need not be stated in ordinary conversation, other times it's controversial or perhaps even false. Consider this argument: in vitro fertilization is immoral because it is unnatural. What's the conclusion of this argument here? Well, hopefully you see the conclusion is in vitro fertilization is immoral. This is what the speaker wants you to agree to. What's the stated premise? What reason has been offered in support of this conclusion? In vitro fertilization is unnatural. But there's an unstated premise here. Again, the unstated premise would be necessary in order to move from the stated premise, in vitro fertilization is unnatural, to the conclusion, in vitro fertilization is immoral. What is that unstated premise? Well, perhaps you already see. Anything which is unnatural is immoral. So here's what the argument is really saying. In vitro fertilization is unnatural. Anything which is unnatural is immoral. Therefore, in vitro fertilization is immoral. But notice that unstated premise, far from being so obvious that it doesn't even require us to state it out loud, it's actually rather controversial, and I think it needs to be scrutinized, right? Anything which is unnatural is immoral. I mean, what about kidney dialysis machines? They seem to be unnatural, or miracle cures, but nobody would want to say those are immoral. I think my microwave is somewhat unnatural, but I don't think there's anything immoral. Don't you take my microwave away from me. Right? So I think we want to examine that. But notice, if I slip it by as an unstated premise, I might get you to accept my conclusion without realizing that it rests upon a controversial premise that should be scrutinized. This is why philosophers, like lawyers, consider unstated premises and conclusions a weakness. Again, it creates vagueness and ambiguity, and it may be a way of papering over an important and controversial claim. Okay, evaluation of arguments. There are two criteria to look at when evaluating an argument. One is the degree of support that the premises give to the conclusion, and second, the quality of the premises. In other words, the truth, the clarity of the premises, etc. But now this idea of support, what kind of support do the premises lend to the conclusion? Well, premises can lend support to conclusions in two importantly different ways. They can be deductive support or inductive support. In deductive arguments, the conclusion is supposed to follow with logical necessity. In a well-formed deductive argument, if the premises are true, the conclusion would have to be, without fail, of necessity, true. But in an inductive argument, the relationship is different. In an inductive argument, the conclusion is supposed to follow with probability. In other words, in a good inductive argument, if the premises were true, they would render the conclusion more probably true. But it's always possible in an inductive argument to move from true premises to a false conclusion. Presumably, that's unlikely if it's a good inductive argument, but it's possible. In a good deductive argument, it's impossible to move from true premises to a false conclusion. So we're going to talk more about that now. So analyzing these two different types of arguments, deductive arguments and inductive arguments, actually requires two different sets of evaluative criteria. And therefore, logic can be seen as being comprised of two parts or two sub-branches, formal logic and informal logic. We'll look at formal logic first. Formal logic is a branch of philosophy which analyzes and evaluates the structure of arguments. Well, that's fine, but what exactly is meant by the structure of an argument? What do you mean when you're talking about the structure of an argument? Well, you've probably seen something that looks like this in your travels, right? All A are B, all B are C. Therefore, what goes where the question marks go? Oh, by the way, side note, the argument on the slide here is what's called a syllogism. And syllogism is just a fancy word that means an argument with two premises and a conclusion. That's all it means. One conclusion, two premises. Kind of a waste of a word, I guess, if you think about it. Now, this happens to be a categorical syllogism because all of the claims in this syllogism are categorical claims. In other words, they're references to categories. Here there are three categories: the category of A, the category of B, and the category of C. So this would be called a categorical syllogism, but the point here is a syllogism is any argument that has two premises and one conclusion. So you've probably done that. What would you logically deduce as the conclusion of this argument? Well, hopefully you would have deduced this: all A are C, right? The conclusion has two, oh, I said that already, oops. Now, what allows you to mentally move from the first two sentences to the third is not the content of the argument. In fact, you don't even know what the content of the argument is, right? The letters are just placeholders for what is as yet unspecified content, right? So you're only looking at structure there. You're not looking at content. Again, you don't know what the content of this argument is. For instance, is the first sentence true? Is it true that every A is a B? You don't know, right? For all we know, there's a A out there that's not a B, right? Again, you don't even know what I'm talking about, right? So like, for instance, I could be talking about Anglicans and Baptists. I could be talking about, I don't know, Australians and bipedal. You don't know what I'm talking about, right? All I said is every A is a B. You don't know what those letters represent. And so you certainly don't know whether it's true or not. You don't know if the second sentence is true. Is every B a C? Same thing goes, right? And you certainly don't know if the third sentence is true either, right? So it can't be the content that is helping you see an important relationship among these sentences. Well, if it's not the content, what is it? I'm telling you it's the structure. Now, you might be tempted to say, why, I don't know anything about those sentences at all. I don't know if the first sentence is true or false. I don't know if the second sentence is true or false. I don't know if the third sentence is true or false. I don't know anything about those sentences. But that's not true. You do know something about those sentences. And I'll give you a hint. What do you know about those sentences? It begins with if. Okay, so what you know is that if the first sentence is true, and if the second sentence is true, then it must be the case that the third sentence is true. Right? That's what you know. Are they true? That you don't know. But you know that if the first two sentences are true, the third sentence, the conclusion must be true. If we were charted all the possible ways the truth value of these sentences might stack up, we could come up with 7 possible combinations. For instance, all the sentences might be true at the same time. On the other hand, all the sentences might be false at the same time. Or one could be true and the other be false and the conclusion true, or it could go any number, well, not any number of ways. It could go 8. No. It could go 7 ways, and only 7 ways. Right? So given this structure, given the structure of this argument, all A are B, all B are C, therefore all A is C, assuming each of those sentences is either a T or an F, there's only 7 possible combinations. The structure will not allow an 8th combination from appearing. Notice on the chart, column 8 is empty. What would go in column 8? TTF. But that's precisely what the structure will not allow. The structure will not allow you to move from all true premises to a false conclusion. Now, this is what it means to call an argument formally valid. And in our class, formally valid or just valid is a technical term, and we have to be careful of that. Outside of class, you might talk about a valid ID or a valid parking sticker or a valid driver's license. That's fine. In our class, valid has a technical meaning, and it means formally valid. If the premises are true, then the conclusion must be true. It also means that the argument has good form or good structure. The idea of good there being as truth preserving. As long as you only put in truth, you only get out truth, right? You put in crap, you might get out crap, but as long as you only put in truth, you get out truth. So it's truth preserving, good structure. If the premises are true, then the conclusion must be true. So valid means that word, that sentence that begins with if, okay? Pop quiz. If an argument is valid, does that mean that the conclusion is true? No. Valid arguments can have false conclusions. If an argument is valid, does that mean the premises are true? No. Valid arguments can have false conclusions. Can valid arguments have false I think I said that wrong, but you got it. Can valid arguments have false premises? Yes. Can valid arguments have a false conclusion? Yes. Can valid arguments have false premises and a false conclusion? Yes. Can valid arguments have all true premises and a false conclusion? No. That's the one combination that's outlawed, right? The other ones could go. So when I tell you the argument is valid, I mean it's 1 through 7. When I tell you an argument's valid, I mean it's not 8, okay? But that's all I've told you. So that doesn't mean you should believe the conclusion, doesn't mean you should believe the premises. I've only said there's a formal arrangement between the premises and the conclusion such that it rules out combination 8. But I didn't tell you which of 1 through 7 the argument is. Let's go back. Can a valid argument have a false conclusion? Well, we've already said the answer to that question is yes. But if a valid argument has a false conclusion, what else do you know about that valid argument? Hopefully you see it means at least one of the premises must be false. So you can't get to a false conclusion unless falsity occurs earlier in the argument. Either both the premises are false or at least one of the premises are false. But if the argument's valid and the conclusion false, then at least one of the premises have to be false. So Aristotle discovered that there are certain argument forms which, if the premises are true, the conclusion has to be true. They are truth preserving and they will not allow you to go from truth to falsity. So his idea was these are the kinds of arguments we want to use all the time. We want to use these valid arguments, these truth preserving arguments. In fact, when he makes his recommendations for how we should conduct science and philosophical inquiry, he would like us to use exclusively categorical syllogisms that are arranged in valid structures. That may not really be feasible for science. That's a topic for another day. But this was early on discovered in philosophy. So formal logic seeks to analyze and evaluate the structure of arguments, as we've already noted. Is not interested in what the argument is about so much as it's interested in the form of the argument. This is the reason behind symbolizing arguments. This is why if you've taken a course in formal logic, you do things like all A are B, or if P, then Q. Why with the letters? What are you doing with the letters? Well, because you're really not interested in what the argument is about. You're interested in a formal relationship between the premises of the argument and the conclusion. So again, when you're learning mathematics, you're in kindergarten, you go, oh, look, 1 cookie plus 2 cookies equals 3 cookies. They go, oh, 1 kitten plus 2 kittens equals 3 kittens. You know, oh, 1 penny plus 2 pennies equals 3 pennies. But eventually, when you graduate, you do away with the things, and you're just interested in the numerical relations. 1 plus 2 is 3. And so we symbolize in math in the same way we symbolize in formal logic, because we're looking at the formal relations among these formal elements. Here are 4 valid argument forms. These are not categorical syllogisms. They're syllogisms, but they're not categorical syllogisms. The first one is entitled modus ponens. And it's this structure, maybe you've seen it before. If P, then Q, P, therefore Q. And what this is saying here is if the proposition P is true, then the proposition Q must be true. And then you add to that, oh, and the proposition P is in fact true. Well, then it must be the case that the proposition Q is true. Here's an example. If there were nothing wrong with terminating the life of embryos, then there is nothing wrong with terminating the life of fetuses. There is nothing wrong with terminating the life of embryos. Therefore, there's nothing wrong with terminating the life of fetuses. Modus tollens starts with the same conditional. If P, then Q. If P is true, then Q is true. If the proposition P is correct, then the proposition Q is also correct. But here, instead of saying the proposition P is correct, it says something different. It says, the proposition Q is not correct. It is not true. Well, if that's the case, then it must also be the case that P is not true. So again, what it's saying is if P is true, then Q is true, but Q is not true. Therefore, P is not true. Again, this is called modus tollens. So we can start with the same conditional. If there's nothing wrong with terminating the life of embryos, then there's nothing wrong with terminating the life of fetuses. But there is something wrong with terminating the life of fetuses. Therefore, there is something wrong with terminating the life of embryos. So this would be an example where we move from the same conditional, but we deny the second half, what's called the consequent. And by denying the consequent, we arrive at the conclusion that the antecedent, the first part, was false. Let's just take a look at that again. So if P, then Q, deny the consequent, not Q, and arrive at the denial of the antecedent, not P. A disjunctive syllogism, number 3. I'm saying either P is true or Q is true, okay? And then I add to that, oh, but not P. P isn't the one. Well, if that's the case, then it follows that Q is true. Either we must accept millions of Americans living without health care, or we must support a universal healthcare system. But we cannot accept having millions of Americans living without healthcare. Therefore, we must support a universal healthcare system. Let me back up just so you see how that looks again. Either P or Q, not P, therefore not Q. I'm sorry, I said that wrong. Let me try again. If P, either P or Q, not P, therefore Q. Think of it this way. If I have two cups and I know the marble is under one or the other, I go, oh, it's not there, then where must it be? There, okay? Fourth and final one that we'll look at briefly, the hypothetical syllogism. If P is true, then Q must be true. And if Q is true, then R must be true. Therefore, if P is true, then R must be true. If suicide is morally permissible, then passive euthanasia is morally permissible. If passive euthanasia is morally permissible, then active euthanasia is morally permissible. Therefore, if suicide is morally permissible, then active euthanasia is morally permissible. Now, notice a couple of things. Number one, it's three conditionals. If P, then Q, if Q, then R, therefore, if P, then R. Sometimes it's called a chain argument. You can see why it might be called that. I'm calling it a hypothetical syllogism, which is also a name it's known by, but you could also call it a chain argument. So notice we have the three conditionals here. Notice something else. You might know what passive euthanasia is and how it is different from active euthanasia, but you don't have to know that the argument is formally valid. Again, the meanings of the sentences is less critical here because what you're looking at is the formal arrangements between the elements of the sentences and how they've been arranged. Again, that's why it's called formal logic. And then finally, I'm not claiming that the first sentence is true, and I'm not claiming the second sentence is true, and I'm not claiming the third sentence is true. As is the case with all of the arguments we've been looking at, I've merely been saying that if the premises were true, then the conclusion would have to be true. So again, I'm not in fact arguing for the conclusions or the premises of any of these arguments. I'm merely giving them as examples of valid arguments. That means it's 1 through 7, but which of the 1 through 7 we haven't established yet. However, note further that if you think the conclusion of any of those arguments is false, then it would be incumbent upon you to tell which of the premises you believe to be false or why. So if you want to say, oh, I think the conclusion of argument number 3 is false, okay, but then you have to show me which of those premises is false. It has to be 1 or 2 or perhaps both. But you can't say, well, I think the premises are true, and I think that if the premises are true, the conclusion would have to be true, but I think the conclusion is false. That doesn't go together, right? Okay, so remember, rational support comes in 2 varieties, deductive support and inductive support. So we're going to move on now to the second, inductive support. And inductive support is something that we look at through a sub-branch of logic called informal logic. Informal logic is a branch of philosophy which analyzes and evaluates the strength and weaknesses of inductive inferences. So in the field of inductive reasoning, informal logic, we do not use the technical term valid or invalid. Those don't apply in this field. Those are exclusively used in the realm of formal logic and deductive reasoning. For inductive reasoning and informal logic, we use the terms strong and weak. Notice something else, that when it comes to deductive arguments, you only have 2 options. Either it's valid or invalid. There's no in between, right? And so it's one or the other, and it can't be both. Right? But in inductive arguments admits of degrees. So you could have a strong inductive inference or a weak inductive inference, or a very strong inductive inference or a very weak inductive inference, or a very, very, very strong. So you get the idea, there's grades, right? And they exist on a spectrum, unlike formal logic and deductive reasoning. In an inductively strong argument, the conclusion is made more likely by the truth of the premises. However, even in a strong inductive inference, it's possible for the conclusion to be false, even when the premises are true. With a strong inductive argument, however, it would be a safer bet to conclude that to assume the conclusion is true. So but it's not a sure thing, right? So that's the nature of an inductive inference. A strong inductive inference is supposed to establish that the conclusion is a safe bet, but it may not be a sure thing, okay? What's an example? Well, most American college professors attended college as students. Kenton Harris is an American college professor. Therefore, Kenton Harris attended college as a student. Well, the premises are true. And I think conjoining those premises, you have good reason to conclude that Kenton Harris actually did attend college as a student. And if you concluded that, you would be correct, right? Why? Well, most American college professors did. Kenton Harris is an American college professor. And as it turns out, for other reasons, I happen to know that I did, in fact, attend college, right? But if you came to that belief based on the premise set, that would be a reasonable inference, a reasonable inductive inference. But consider this example. Most American college professors attended college as students. René Louis is an American college professor. Therefore, René Louis attended college as a student. Again, on the face of it, this looks like exactly the same argument and giving you exactly the same good reason to accept the conclusion. However, as a bit of background belief that I have and you don't, I happen to know that the conclusion is false, right? René Louis happens to be a dance practitioner and teaches dance at colleges and universities around the country, actually, but never actually attended college as a student. And his teaching position is based on his abilities and his demonstrated knowledge in the field as a practitioner of dance. So that happens to be the case that I happen to know. So it happens that Professor Louis is a dance practitioner who never attended college. In each, both of the two that preceded, the conclusion follows inductively, but not deductively. The premises, if true, would make the conclusion more likely, but the premises could be true and the conclusion false. Further, notice something else about inductive evidence or inductive inferences. It's always possible that some additional information will be learned, which will undercut the strength of the inference. So again, you had good reason to believe that René Louis had attended college as a professor. Why? Because you knew him, as a student rather, because you knew him to be a college professor. But I can undercut that belief when I say, but he's a dance practitioner and he's never actually gone to college. Well, there you go, right? So additional information can always undermine the confidence you have in any inductive inference. It doesn't work that way with deductive inferences. Again, no new set of facts are going to change the confidence you have in the conclusion if the premises are true. Now, of course, if the premises are false, that's another story. But if you know the premises to be true, you can be 100% confident that the conclusion is true and that won't be overturned by additional information. That's the nature of deductive belief and deductive inferences. It's not the nature of inductive belief or inductive inferences. So inductive arguments always admit of degrees. I mentioned that already. Inductive inferences are always quantified inferences and always approximate. So we might say a 90% chance of being true, or a strong inference, 70% chance of being true, follows but weakly, 51% chance follows but very weakly, 50% chance or lower, doesn't really follow at all. Typically, the minimal requirement for a good inference, an inductive inference that is to, in order to support a position, is to show that it raises the probability at least to 50%, right? However, notice this: if the initial probability of the truth of the conclusion is low, let's say it's only 20%, and then my argument raises the probability of the conclusion to 50%, well, then I've given a good inductive argument. Why? Well, because I've raised the probability of the conclusion. I've raised it significantly. I've raised it 30%, right? Now, I still haven't made it reasonable for you to accept my conclusion. It's still 50-50, and you might still say, look, I don't know. I'm going to be agnostic on that. It's only a 50% chance. Nevertheless, my argument has been effective because, as I said, it raises it from a low probability of, I'm showing there, 20% to a much higher probability of 50%. So what are some typical inductive arguments? Well, there are 4 that we're going to look at, again, just briefly. Inductive generalizations, arguments by analogy, statistical syllogisms, and abduction. Inductive generalization, something you're probably already very familiar with. This is where one generalizes based on a sample. So you gather information about a certain set of instances, that's your sample. And then on the basis of that, you draw conclusions about the entire set, and that's your target. So in an inductive generalization, you have a sample and a target. Imagine I'm making, spaghetti sauce, and I'm trying to decide whether there's enough oregano in the spaghetti sauce, right? Well, what do? I'll sample the sauce. I'll take a little scoop of a little spoonful of the sauce, a ladleful, a little taste, and I'm sampling it. Why am I sampling it? I'm tasting this to get information about the entire pot, right? So my target is the pot. My sample is whatever ends up in my spoon, right? So for instance, if I say I interview 100 FIU students, and on the basis of those 100 interviews, I draw conclusions about all FIU students. In this example, what is my sample? What is my target? Well, hopefully you realize. In this case, my sample would be the 100 students I interviewed, and my target would be all FIU students. So some things to consider about the strength of an inductive generalization, right? Well, here are things you want to consider if you're trying to say, how reliable, how strong is that inductive generalization? The first you might ask is, how many are in the sample? Generally speaking, the more that's in your sample, the better. Too few, and you are in the danger of what's called a hasty generalization. This is a logical fallacy. This is a mistaken reason where you draw unwarranted conclusions because your sample is simply too small, right? So 100 students may seem like a lot, but there are over 6,500 65,000, excuse me, 65,000 FIU students. So 100 students, that may not be sufficient to give you an adequate sampling of your target population. A second question to ask is the sample, the ones who ended up in the spoon, right, the ones that actually got information on, is your sample representative of the entire target? A biased sample is one that is misleading because it is not taken to be typical of the target population. Well, because rather it is taken to be typical of the target population, but in fact, it is not typical of the target. If the sample exhibits relevant characteristics out of proportion to the target, then it's considered a biased sample. For instance, if my target were, say, Miami residents, but then when I look at who ended up in my sample, and the majority of those in my sample are Filipino Americans, well, I have a biased sample. And why is that? Because the majority of Miami residents are not Filipino Americans. And so I have a disproportionate amount of Filipino Americans in my sample as compared to my target. And that might give me misleading results. Likewise, if I were sampling FIU students and I conclude that only 20% of them consider parking to be a problem, you might note that my sample was drawn on the Biscayne Bay. And students on the Biscayne Bay are not representative of the student FIU body at large. So conclusions based on a biased sample are therefore unreliable. Biscayne Bay students is a much smaller percentage of the population of total FIU students. And so if my sample is disproportionately representing the Biscayne Bay, then I may end up getting results which are out of misleading with the concerns, let's say, of the entire student body. Curiously, in 1936, during the election campaign that pitted Franklin Roosevelt against the Republican challenger, Alfred Landon, the American Literary Digest was a magazine that collected mail-in postcards from nearly 1/4 of the voting public and predicted the election results. So notice, getting 1/4 of that's 25%. That sounds a pretty large sample. Based on the collected data, they forecasted Landon would win in a landslide. In actuality, though, it was Roosevelt who won one of the biggest landslides in American history. Roosevelt received 27.7 million votes compared to Landon's 16.6. So what went wrong? Subsequently, it was thought that those who disapproved of the incumbent, Roosevelt, were more motivated to mail their cards than were Roosevelt supporters. And so part of the problem with this poll taking was it was relying on what they call a self-selected sample. The only people that were sampled were the people who were motivated enough to mail in the cards. And it was theorized that the only people motivated enough to mail in the cards were people who were not happy with the way the country was going and weren't happy with the current administration. Others pointed to the fact that the readers of that particular magazine were probably wealthier and more likely to vote Republican than the electorate in general. So again, your sample is biased because it's going to be people with a disproportionately high income relative to your target. In any event, the mistake was so scandalous that the magazine closed shortly thereafter. George Gallup, yes, that Gallup, on the other hand, correctly predicted the election results on a far smaller but more carefully controlled sample. This event is seen as an important one in the refining of scientific polling. Online and call-in polls are particularly at risk of this error because the respondents are self-selected. I mentioned that a moment ago. The people who care most about an issue will respond, sometimes flooding and biasing the poll. This is, for instance, why FIU cannot simply allow people to voluntarily fill out exit surveys when graduating from FIU, because the only people who will fill them out, if it's voluntary, will be those self-selected, and we may not get accurate or reliable results because it's a self-selected group. Some things to consider about generalization. Often what is sought in scientific surveys is a random sample. And a random sample, technical term, is a sample where every member of the target population has an equal chance of being a member of the sample population. So think back to that magazine's mailing in postcards. Well, it's not the case that that would give you a random sample, because not everyone has an equal chance of being a member of it. First of all, you'd have to be a magazine subscriber. Okay, and not every voter was a magazine subscriber. Therefore, anyone who wasn't subscribing to the magazine did not have much of a chance, if any chance at all, of being a member of the sample. So it wasn't a random sample in that regard. But also, in a more subtle way, the only people who would have an equal chance are people who are motivated, right? If you just don't care, or you're kind of happy with the way things are going, and you just don't feel like wasting money on a postage stamp or what have you, well, then you're not going to be part of the sample, even though you are part of the target. But there's no absolute guarantee that even a random sample will in fact be representative. It's more likely that it will be, but it's not a guarantee. So it might be, think about my earlier example, that I did use some sort of method to generate a random sample. I don't know, picking, Miami resident from a list of residents or something like that. But then I might look at it and go, oh, wow, there are more males in this sample than there are in the general population. It's not really a representative sample. Or, oh, there's more Filipino Americans in this than there are in the general population. It's not a representative sample. So random is referring to a method which guarantees that every member of the target has an equal chance of being a member of the sample, but it doesn't guarantee it. It doesn't guarantee a representative sample. Again, it makes it much, much more likely. That's why we do it, but you always have to double check. Pop quiz, why are TV call-in surveys not random surveys? Well, hopefully you see it's because if you're not watching the show or you're not motivated, you're not going to be part of the sample, even though you might be part of the target. So one question, how many in the sample? Another question, is the sample representative? A third question might be this: what margin of error are you building in? For instance, if my survey reveals that 70% of the population were female, my conclusion would be stronger if I more modestly said between 60 and 80% of the target is female. Why is that? Well, because let's say that exactly 70% of the target is. So in other words, my sample was spot on and my sample said 70% and the target is 70% and I was exactly right. Well, what if I was off just a little bit? What if my sample said 70, but the target population is actually only 69, or it's 71, or it's 68, or it's 72, right? So by building in a margin of error, it's more likely that what I'm saying is true. So I could say, well, between 60 and 80% of the target is a female or has this characteristic. Mm-hmm. Now notice though, that what I gain in accuracy, more likely to say what I'm saying is true, strengthening my inductive inference, what I'm gaining in strength, I'm losing in precision. Because rather than saying exactly 70, I've expanded the margin between 60 and 80. A second inductive inference would be arguments by analogy. A simple argument of analogy might go something like this: John was a very capable corporate executive of a large successful business. Therefore, he will make a good director of this large government agency. The idea here is that the jobs are analogous. Thus, his demonstrable skills that allow him to be successful in the one position will allow him to be successful in the other. The more analogous the jobs are, the stronger the inference. The more disanalogous, the weaker the inference. Sometimes it's been thought that someone who was a good corporate leader would also be a good leader of an academic institution. But there are certain very important disanalogies between the way to run a large academic institution and a large corporate institution. There are different cultures and different procedures and different ways of communicating. So that may not be nearly as strong an inference if the jobs are in fact disanalogous and require alternative skill sets. Here's another argument by analogy. In this example, imagine that I know that several individuals have certain characteristics in common, characteristics 1 through 6 in common. And then another individual is known to share characteristics 1 through 5. And I therefore conclude that that additional individual also has characteristic 6. This is a little abstract. Let's be a little more specific. Say members of our sample have 6 properties in common. The target individual is known to share some of the properties, 5 of the 6. And on that basis, you conclude that the target individual will also share the 6th unknown property. For instance, imagine that Mary, Sue, and John are all FIU students. They're all math majors. They all have GPAs of 3.75 or better. They all attended Miami Senior High School. They all took calculus their first semester at FIU and passed with an A. They all did well on the LSAT, and they all got an A in logic. Now I come across Bill, and I see that Bill is also a math major. Bill is also got a GPA of a 3.7. Bill also attended Miami Senior High School. Bill also earned an A in calculus his first semester here at FIU. Bill also did well on the SAT. And I say, well then, he has 1 through 5 in common with the earlier group. He'll probably have number 6 in common as well. Bill will probably get an A in logic. So there's another example of an argument by analogy. Now, certain things to consider about an argument of analogy. Again, how many in the sample? As a general rule, the more the better, right? So the more people who have all of the shared properties, it strengthens your inference. I mean, imagine that one of the group didn't get an A in logic. Well, then that would weaken my inference, right? But if there was a 4th or 5th or even 6th individual who all shared properties 1 through 6, well, then that would strengthen my analogy. Again, the larger the sample, the better. What percentage of the sample has the unknown quality? Again, how many of the sample all got an A in logic? Notice if Mary did not get an A in logic, the argument would be weaker. It still would be an okay argument. You got 2 out of the 3, but it weakens the inference. What is the number of relevant similarities that they have in common? The more the better, right? Oh, they all had the same high school. Oh, they all got an A in calculus. Oh, they all have a high GPA. Whoops. So notice if they all had the same professor. I didn't mention that in the previous criteria, but if they all had the same professor, that would strengthen the analogy as well. But of course, the question of relevant similarities raises the question of what is it to be a relevant similar property? To raise the probability, the similarity must be relevant to the possession of the unknown quality. In this case, for instance, being blonde. So let's say every member of the sample population was blonde, but that's irrelevant. It doesn't make a difference to whether you're going to get an A or logic or not. Now, how do I know that? Background beliefs, right? That's something I bring to the premise set. So again, a difference between inductive and deductive logic is in deductive logic, you only have to pay attention to the premises that are right before you. In inductive logic, background beliefs, things that you bring, new information that you gain and learn later on, they could all make a difference, strengthening or weakening the inductive inference. This is just one example where background knowledge is necessary to evaluate the strength of the inductive inference. The relation of the premise set to the conclusion is an informal one, and it's never merely a matter of form. Again, this is why it's informal logic, not formal logic. Curiously, playing a musical instrument is a relevant consideration. It has been shown that students with musical training perform better at logical reasoning tasks on average than do those without musical training. Who knew? But that's the point. If you do not already know that musical training is relevant to your performance in logic, then you wouldn't recognize having musical training as being a relevant characteristic to the inference. Some things to consider again about arguments from analogy. We mentioned how many in the sample, the percentage of the sample that has the unknown quality, what is the number of relevant similarities, but then finally, is there diversity among the properties unshared with the target with respect to the sample population? The greater, the better. What do I mean by that? Well, what if Mary and John were from France and Sue was from Japan, and we don't know where Bill was from? Well, that would be a stronger inference because nationality wouldn't be relevant since that's an unshared quality. So Bill may share nationality with Mary and John, or perhaps with Sue, or maybe with none of them. But evidently that's not relevant because in this inference, they don't all have that property in common. Some things to consider. Oh, I said that already. Number 3, statistical syllogism. Statistical syllogism, pretty easy to understand. If I said n% of A's are B's, K is an A, therefore there's an n% probability of K is a B. Right? What do I have in mind here? Well, if I said 90% of Swedes can swim, Bjorn is a Swede, therefore there's a 90% chance that Bjorn can swim. Or if I said 85% of Americans believe in God, Bill is an American, therefore there's an 85% chance that Bill believes in God. Right? That's the nature of a statistical syllogism. But again, background beliefs or new knowledge gained can undermine the strength of that statistical inference. Let's say you know as part of your background beliefs that Bjorn is paralyzed. He's disabled in a certain way. Well, that would undercut the confidence you have in the conclusion. The probability of the conclusion is not a result of the formal relation between it and the premise set, as already noted. The support is an informal relation, and between it and the entire body of known facts. The premise set constituting only those of momentary focus, and we may always expand our focus to include more beliefs which have not been immediately explicitly stated. The fourth and final kind of inductive inference we're going to look at is abduction. Abduction, this is sometimes referred to as inference to the best explanation. We begin with a set of facts which we know to be true. Then we hypothesize H as the best explanation of the facts F, and therefore we conclude that H is true. For instance, I hear a crash in the other room. I go in and I see my cat run through an otherwise unoccupied room. I see that there is a smashed glass vase on the floor, and I form the hypothesis my cat knocked over the vase. So I have reason to believe the conclusion, my cat knocked over the vase, and why is that? It's the best explanation for the facts in evidence. Again, this is abduction or inference to the best explanation. Now, we have to be wary when we're doing inference to the best explanation. First of all, we have to ask, do the facts actually require an explanation? Sometimes there are simple coincidences which don't in fact need to be explained. This is a faded cultural reference, but the two Darrens on Bewitched, right? Well, nothing needs to be offered to explain why that happened. It just was a coincidence that they ended up replacing the actor in the 6th season of the series. Second, sometimes even the best explanation is actually not that good and is somewhat far-fetched, right? And third, there might be more than one nearly as good explanation among the rivals. So imagine I have 3 rival explanations for the same set of facts, A, B, and C. Well, in the example I've given you, A has a 30% chance of being true, B has a 40% chance of being true, and C has a 30% chance of being true. But notice, B is the best explanation. Does that mean I should believe it? I don't think in this case. Why? Well, number one, it's still less than 50%. There's still a 60% chance it's false. And beyond that, it's not that much better than 2 rivals, which are nearly as good. Okay, so the last little thing I'm doing is just because I think it's fun, and it's taken from a game show that was popular when I was a boy, believe it or not, Let's Make a Deal. I think it has been revived and it's now currently on daytime TV, but there's a very big game show on daytime TV when I was growing up and starred Monty Hall, who was a Canadian game show host. So always near the end of the Let's Make a Deal episode, the person who had won various contests so far would be shown 3 curtains: curtain number 1, curtain number 2, curtain number 3. And Monty Hall, the host, would say, of these 3, pick one. Now, behind one of these curtains would be some fabulous prize. I don't know, like a luxury car, maybe a boat or something like that, a vacation to Spain. But behind one of these curtains, but only one, there is some fabulous prize. Behind 2 of them is some sort of silly booby prize that is not really a prize at all, right? So Monty Hall would always give the contestant a chance to pick one of the 3. But then the way the game was played is after the contestant would pick one of the 3, then, and let's say you're the contestant, and let's say from the options you choose curtain number 1. So Monty, I pick curtain number 1. Again, we know that there's an equal chance that the prize is behind curtain number 1 or curtain number 2 or curtain number 3. So as it stands, each curtain has about 1/3 chance of being success, 2/3 chance of being the wrong one. Now, as would always happen, Monty would open one curtain, and he would open a curtain that he knew did not have the luxury prize behind it, right? And so zonk, right, he opens a curtain. Let's say he opens curtain number 3, and it turns out that curtain number 3, there's a goat, right? So that's Carol Merrill, who is a spokeswoman or, kind of spokesmodel on the show. Anyway, so he would open one curtain that he knew did not have the prize. In this case, it's curtain number 3. Then he would give the contestant, that's you, an opportunity. So would you like now to change your guess from curtain number 1 to curtain number 2? Right? He's giving you an opportunity to change from curtain number 1 to curtain number 2. Should you change from curtain number 1 to curtain number 2? Well, the answer is yes, you should. Based on probability theory. Yes. And why is that? Well, because when you chose curtain number 1, I spelled that wrong, the probability that the car being behind curtain number 1 was 1 in 3. And the probability of it not being behind curtain number 1 was 2 in 3. So you had a very good chance it was not behind the curtain you chose, only a 1 in 3 chance that it was. Now he shows you the goat behind curtain number 3. But notice that does not improve your odds of having been right the first time. He would have shown you the goat in any case. That means that it doesn't diminish the odds that it's not behind curtain number 1. So in other words, the chances of it being behind curtain number 1 is still 1 in 3. Now, some people think, oh no, isn't it 50-50? No, it's not 50-50 because when you selected it, it was 1 in 3 and nothing has changed. So notice the likelihood that it is not behind number 1 is still 2 in 3. That's still the likelihood. Therefore, it does raise the probability of the odds of it being behind number 2. And it raises it not to 50%. It raises the chances that it's behind curtain number 2 to 2 in 3. There's a 2/3 chance that it's behind number 2. That's why you should pick it. You go, well, how does that work exactly? Well, because the odds of it not being behind number 1, that is not 1, is still 2 to 3. That's what they were. That's what they still are. Now we add new information. It's not behind number 3. But the new information that it's not behind number 3 doesn't raise the probability that it is behind number 1. Given the new information, the odds of it being behind curtain number 3 is 0. And the odds of it being behind curtain number 2 alone is 2/3. Because notice, if we think of it as hypothesis H as it's behind number 1, and hypothesis not H, it is not behind number 1, hypothesis not H started with a 2/3 probability of being true. Well, that's still the case, except now instead of hypothesis not H being 2n or 3, we have new information. Now not H equals 2, right? Why? Because we're looking at 3, it's empty, we got a goat. Think of it this way. Had you originally been given the choice to pick either curtain number 1 or both curtain number 1 and curtain number 2, you certainly would have chosen the second. You said, oh, Monty, I'm going to take curtain number 1 and curtain number 2. Right? Why? Well, by taking curtain number 1 and curtain number 2, you have a 2/3 chance of being correct and only 1/3 chance of being incorrect. The hypothesis H, that the car is behind number 1, is 33%, while the hypothesis that it's not is 66%. So the probability of the hypothesis equals of H equals the probability of not H times 2. Well, nothing's changed. Showing you the goat does nothing to change the probability that you were wrong when you chose curtain number 1. It would have shown you the goat in any event. Therefore, there's still only a 33% chance that you were right when you chose it. There's still a 66% chance that you were wrong when you chose it. Bottom line, change your choice. But our intuitions on probability are somewhat unreliable. So I owe this example to Paul Draper. He may have gotten it from someplace else. Paul Draper is a former colleague of mine. He's now at the University of Purdue. And he told me once that he could drink free at a bar all night long by exploiting this unintuitive probability strategy. So the notes I've given you have a few other bits of information that I've not included in this power presentation. I think it's probably long enough. And I hope that it has been useful to you. Naturally, if you have questions on anything I've said, you certainly can email me, or we could set up an appointment either virtually or face-to-face where we might talk about whatever questions or concerns you have. So have a good rest of your day.